the sand is pouring from a pipe at the rate of 16 cubic feet per second. Well, when I always did word problems, I always tried to find the numbers because I knew I'd do something with them. If the falling sand forms a conical pile on the ground whose altitude is always 1/4 of the diameter of the base, how fast is the altitude increasing when the pile is 4 feet high? So all of that has to go down here into my problem. Mm-hmm. Yes. Okay, so look and see what you got. Put some numbers in. What am I given? What do I want to find? Give you a second to try it. In cubic feet per second. It's the change in the volume over the change in the time. Mm-hmm. We'll do it, yeah. Okay, so let me get up here what we have. Height. Altitude is height. Okay, so we have 16 cubic feet. If I put the units in, that helps me per second. Right? Well, that's the change in the volume. Just think of that D as a delta, because that's what it is. It's a tiny, tiny change. And the seconds is a measure of time. So that gives us our variables. And it says the falling sand, says altitude. Well, I need an altitude here. So would you like to call this altitude, what letter? H. Well, I'd rather use H because I'm looking at my formula. And then this is the what? That's the radius. You know that the pile will start small like this, and then it's going to get bigger, as more sand. So both the radius is changing and the height is changing. You ever seen sand form in a conical pile? Okay, so the base is going to get bigger, but it's also going to grow in height. Correct? The radius is not constant. Okay, so it says the altitude, which is h, is always 1/4 of the diameter. Called D for diameter. What's the diameter equal to? 2 times the radius. So substituting that in here, then h is equal to 1/4 of twice the radius. What fraction is that? That's right. H equals 1/2 of r. Okay, Tom? Write it down. Okay. How fast is the altitude increasing? What's that question asking me? I want the change in what? Volume. That's right. Altitude, change in height as time changes. And it says when the pile is 4 feet high. What is 4 feet? H. H equals 4 feet. And this is the whole secret. By putting these in here, it tells me what letters I want to keep in my problem. I need to keep an H and a V. There's the V, there's the H. What do I want to eliminate? No, the R. Because I want volume in terms of just one variable. I don't want 2 variables in there. I've got 2. And I could do 2 variables, but then I'd have to use the product rule because both R is changing and H is changing. So I want to get rid of R. Well, I have this. H equals 1/2 of R. So what's R equal to? 2H. And now, that's to me when it gets the easy part. So I'm going to rewrite my volume formula because I know what it is. It's 1/3 pi r squared h. And I'm going to put this r right in there for that r. I have not done any derivatives. I'm just getting the volume in terms of the height. Now usually it's a similar triangle. In this case, r was always is some function of h, and it just depends on the problem. I've seen some problems like this on the exam. Almost exactly the same problem. So in place of r, I'm going to put in 2h. And then I'm going to square it. And then, are you going to take the derivative now? No, you are going to simplify that. So Vm equals 1/3 of pi, not skipping any step, plus 2h quantity squared. Or h squared times h. Derivative now? No. What should I do with these h's? Multiply them out. So volume equals, whoops, I need a pen. Well, it's 1/3 pi times 4, and it's h to the what? 3. Can you write that as a one fraction? Because it's just messy looking. It's 4 pi over 3. Is that okay? That's just arithmetic, but that's okay. We have questions, we have questions. Okay. Did we forget what we're doing? Yep, I need to do a derivative. Because I know what the derivative is. It's 16 cubic feet per second. So let's take the derivative of both sides. Now that's just a number. Remember, we can ignore those numbers. And with respect to what? Time. Somebody may want to use a v prime and an h prime, but I don't like that because it doesn't say what the derivative is with respect to. That really makes a difference. dv dt equals 4 pi over 3. What's the derivative of h cubed?
3 squared.
Times. Now that you did the cubing part. Now you got to do the inside, dh dt. And then we simplify before I even put anything in. What can I get rid of? I can get rid of some stuff, right? I can get rid of the 3. What do you mean get rid of it? I pass it through the operator. Do you remember when I take the derivative with respect to x or t of k times f of t? We'll do it this way. That's equal to k times df dt plus product rule f of t times the derivative of k with respect to t. What's that equal to? What's the derivative? Yeah, it's 0. So this term isn't there. So you can just pull the k right through there. Is that okay? Okay, get some numbers in. I'll turn this monitor around. I forgot to do that. Okay, and what are we putting in for numbers? dv dt is, I don't know what dv dt is. 16. I'm not going to put my, I could, but I'm not going to put my units in. That's weird. Equals 4 times pi. H was, I want it at the instant. So at 4 feet, I'm going to take my picture. So that's at 4, which we're going to square it, and dh dt. I think sometimes we have more issues with solving for dh dt than we do with the rest of the problem. Oh, it's icky. Okay, where did what come from? Oh, okay. So 16 equals 4 pi times 16. And I'm lazy. I don't want to get my calculator out. I see a 16 on both sides. What can I do with them? I can cancel them. Goes in once. We're still left with a 1. So dh dt is 1 over 4 pi. Yeah, it is what we got yesterday. Interesting, we got the same answer.
Was that the same?
Nope. Just happened to be the same answer. Do I need to do a quick poll? See if you guys get this? This is going to be a yes or no. Or do you want the green one again? Okay. What's the question? Do you feel more comfortable with related rates? I'm sorry, I should have written that on there. After this problem. Are you getting more comfortable with related rates? Well, or did you understand this problem? Because this problem, yeah, we have three, don't I? Don't I have three? Oh, we have some toughies coming up. This is just like, the quiz could be anything like these things. Remember, if I do it in class, it's probably pretty important.
We're just practicing here.
We're practicing. We do have an assignment out of the book on the bottom.
Yeah. Like, are we learning more today? Or?
No, it's just more of the same.
Okay, good.
Okay. Looks pretty good. Maybe we could just leave it open. Let's see what happens if I leave that open. Okay. Oh. Ready? Light in a lighthouse. Now, the problem with this problem, and there's one in the book that's just like it, is that it's just hard to visualize what's happening. We're in an airplane or a helicopter, and we're looking down at the top of the lighthouse. So we're in a helicopter above Split Rock Lighthouse. And over here is the shoreline. There's the top of the lighthouse. Actually, Split Rock's not in the water, but that's okay. But anyway, this lighthouse is 1 kilometer offshore from a straight shoreline, and it's rotating at 2 revolutions per minute. And I shouldn't have this 1/2 kilometer here. This should be 1 kilometer. Because it says, remember what we want to do, label things that are fixed. That lighthouse isn't moving, and the shore is not moving either. Okay? It's rotating around at 2 revolutions per minute. So it's doing this. Now you've seen some of those old war pictures, maybe not anymore, when they have the guys trying to escape from the prisoner camps, and the light would start here and it would go down the shoreline. And then the light would go out and it'd be out on the water, and then it would come back around here. Do you remember seeing movies like that where you see the light going down the fence? They're old war movies. There's some really great ones. The Longest Day is one of them. Great movie. Because we are in the air, we're looking down. So here's the land, and this is the top of the, this is all water here. This is the top of the lighthouse. Yes, we're looking down. We're in a helicopter. We're just looking down, and you're seeing the top of the lighthouse, the land's over there, and you're watching the light go down the shoreline. So we're going to get a triangle. That's why I said this one's kind of tricky because it's just hard to comprehend. See the picture. But anyways, rotating at 2 revolutions per minute. 2 revolutions per 1 minute. This one's a little tricky because of that. I'm at least going to write it down. I'm not sure what I'm going to do with it. How fast is the beam moving along the shoreline? So we're going to take a snapshot. And right now in our snapshot, the beam is right there. What would you like to call that distance? X. This is fixed. This is 1 kilometer. I don't know why I have a half there. I guess I'm looking at how fast is the beam when it passes the point? 1/2 kilometer from the point opposite the lighthouse. Not sure where the one. Oh no, we do. Well, we have to look at the revolutions per minute. I'm not reading it right. What are you going to do with the revolutions per minute? Yeah, we have to change it. Okay, I got the 1/2. Okay. We have to change the 2 revolutions. 1 revolution equals how many radians? 1 revolution goes around a full circle. How many radians is that? 2 pi radians. So I want to change this. The one in the book is easier. This one's trickier. So it's 2 revolutions per minute. Well, 1 revolution is 2 pi. Let's do it this way. It's 2 pi radians. I'm going to actually put the word in there, per revolution. So if I simplify that, what do I get? 2 pi radians equals 1 revolution, right? So what are you going to do with these? You're going to multiply it. So it's 4 pi radians per minute. What is that? Radians is the change in the what? What's radian a measure of? It's the velocity of what, though? Radians is a measure of what? Angles. So that's the change in my angle as what changes? Time. So the light's doing this. I'll get dizzy if I turn around, but it's doing this, right? You want to see me fall. Okay, so the light's just going down here. See the angle's changing? Which angle is that?
Theta.
It's this one, right? Good name, theta. And it says when, and that was the part I was a little confused about, it says when it passes the point 1/2 kilometer from the point opposite lighthouse. Now my head is working. So it's when this distance, here's this point here, it's when this distance is 1/2. So x is equal to 1/2. I'll show you what I'm going to do with that triangle. You guys all have calculators, so you could use them.
What do we have to
What do we want to find? How fast is the beam moving along the shoreline? What do you want to find? How fast is this beam moving? What is that? The change in what? Yeah, that's dx dt. If we get this part down, then we can do the next part. Might we have a question? Oh, okay. So, I always go back here. What do I want to relate? X and what? Theta. I don't want to do Pythagorean's theorem. You know why? I don't know anything about the hypotenuse. Oh, yes, I do. I've got theta, and I have x, and I have the 1. Think trig.
theta?
Tangent. The tangent of theta is equal to what?
X over
X over this distance, and that distance is constant, which is 1. So when I go back and figure out what relationship I want, I go back and I look at my dx dt or whatever I have in the find and given, and that's what tells me I have a theta and an x. I don't want to use Pythagorean's theorem. I can use trigonometry. I don't want to use the sine either, because you know what? I don't know the side. It can be done. Let me tell you, it's pretty ugly to do it that way. This is much cleaner. Is that okay? Alexis, is that okay? Okay. Now what are we going to do with this? The tangent of theta equals x. I have to do the derivative. You're in calculus class, but I have to do the derivative. The good news about the final exam is it's going to be limits and derivatives. The AP exam, you're going to have limits, derivatives, and antiderivatives. So you'll have to make up your mind as to what it's going to be. But on this final, that's what's it's called an integral.
Wait, so this stuff is not on the final.
Yeah, this is on the final.
You just said it's just
This is still derivatives. Antiderivatives are not on the final. But when you take the AP exam, it'll be everything. So it's just, don't forget to study your limits. Okay, so what is the derivative of the tangent function? Yeah. I could do sine, cosine, cotangent. I could do any one of those, except the only ones that I have information on are the x's here. Is this guy, and that angle. That's it. So I'm going to use what I have in my picture. So it's secant squared of my angle. Somebody remembered. You know, by the AP time, you're going to have to know those by heart. Times, and then you have to take the derivative of the inside function. D, what's the derivative of theta? D theta dt. And I like the right side. It's just what? Dx dt. And that's what I want to find. Oh, that's not too bad, right? That's what I want to find, dx dt.
Oh, so that's it?
We'll get there.
Wait, so now we're done?
No, we got to substitute stuff in. I got to find the secant of my angle when x is a half. So let me draw my triangle here. We don't even need to know what theta is. This is 1, and this is 1/2, and here's theta. Can I find the secant of theta? I could find theta. You have a calculator. You could. Well, I mean, inverse tangent, tell me what it is. I could find the secant of theta because what's the secant of theta? What's the cosine of theta? 1 over the hypotenuse. What's the secant of theta? Hypotenuse over 1. I have to find the hypotenuse. And I don't want to deal with 1/2. And I don't want to deal with fractions. So guess what I'm going to do? I'm going to use the principle of the reduced triangle, but I'm not. I'm going to make a big triangle, because I'm not going to really make it bigger. I'm going to make this twice as big. So what would this leg be? 2. This would be 1. Now this is easy. And I don't even have to go back to the original triangle. If I don't want to, let's see. Square root of what? 5. Since these are similar triangles, I can find the secant of my new triangle. Because it's the same thing. It's the square root of 5 over 2. See, if I go back to this, this is the square root of 5/2. They're similar triangles. It has to be the same. Okay, so it's the square root of 5 over 2 is the secant. A lot of stuff going on. What are we going to do with this? The secant squared times the theta dt. Oh, we know what that is. That's 4 pi radians per minute. Times 4 pi equals dx dt. And we can simplify that. That's right, 5 over 4 times 4 pi. That's right. Nope, it won't be revolutions, because dx dt is how many feet down and down the shoreline. You're not finding an angle. The one in the book isn't in revolutions, it's in radians. Now, in a minute, it goes around twice. It's pretty fast. We've had Ferris wheel problems that have gone 2 radians per second, which means you'd be flying off the Ferris wheel. Okay? Did the poll change? Okay, so we're going to... Yes, it is. Well, you have to use different variables. Mm-hmm. Okay. At least I wrote this question this time. Hey, where's all my stuff? Oh, there it is. So I'm okay with it. I'm not like totally lost, but I'm not like I can do this problem. But there's one in the homework that's just like it. No, in the book set. And I took out some of the other problems on the worksheet, which are nice to do. So Thursday's kind of your day. We'll go over the quiz and your day to ask questions on anything. Now, you know, if you want, there's calculus in 20 minutes. Let me put a blank sheet up here. On YouTube, calculus in 20 minutes. I highly recommend you watch that, but don't watch 20 minutes. You only need how many minutes? We've only done half the curriculum, 10. And it's kind of entertaining, but it'll get your mind going about all the different things we've done. And then you're going to go back and say, oh yeah, now I remember intermediate value theorem. I better go look that up because I don't know what that is. You know, and of course we'll be here for extra help too. So, like anybody comes in, I have candy, nobody even comes in. Okay, how are we doing this one? Okay, not so good on that last one. You don't like the angles. But remember, you find you're fine and you're given, you look there and it tells you what variables you want to use. If it's an angle, it'll tell you that. Okay, here's another one. A person standing on the cliff. Don't you love my pictures? Oh, there's the worksheet answers. Nice. You want to try this on your own?
Yeah.
Okay. You want me to read it? Sometimes it helps for somebody to read it. A person standing on a cliff is watching a motorboat. Okay, I have a sailboat. Through a telescope as it approaches the shore directly below her. Cowgirl. The telescope is 250 feet above the water level, and the boat is approaching at 20 feet per second. At what rate is the angle of the telescope changing when the boat is 250 feet from shore? So you do your find, give, and when.
Oh, there's no paper.
No, I know.
Hey, shucks.
You might need another piece of paper.
But I think